This is the Fields Postdoc Colloquium, and let me remind you all that we have a variety of people from different areas of mathematics. This is an opportunity to learn what everybody else is doing. We ask the speaker to give a very accessible talk, and we invite the audience to ask lots of questions in order to make sure that they're keeping us all grounded and letting us know what they're doing. And this time looks really like we're gonna have some really nice pictures to look at. So Nick, discrete surface geometry and intrinsic triangulations.
Awesome. Thank you for the introduction. Thank you for everyone who's here. Obviously, since we are a really small group today, please don't hesitate at all to ask any questions, and this can be more of a conversation, but one way or another, this should be fun. Also, disclaimer, we frantically exported my slides from Keynote to PowerPoint in the 5 minutes before this talk. So if we hit broken fonts at some point or something like that, I apologize. I think we should be good to go though. So let's get started. So I think this talk is a little bit more on the applied mathematics side than some we've had in the past week. So I wanted to really quickly just set the stage about the kinds of problems we're interested in solving before I go into some of the mathematical techniques we use to solve them. So this work gets applied to a field called geometry processing. And in geometry processing, we take all of these exciting kinds of 3D data that exist in the world. So things like 3D scans, technical assets, AR and VR stuff, scientific medical imaging data, and so on. And we have all these things we want to do with that data, different applications, like animating them and allowing artists to manipulate them with creative tools, to machine learning on 3D geometry and things like that. And so geometry processing here is sort of the blanket field for all of the different kinds of things we want to do to that data to put it to work for those tasks. So these ends up being both sort of mathematical formalisms for things like parameterization and shape priors and PDEs on surfaces and things like that, as well as the computational algorithms that let us actually take this kind of data and compute such a thing on it. And in particular, we're going to be most interested in surface meshes because these are what we use most commonly in these kinds of applications to represent 3D shapes. And here I've just shown three sort of arbitrary examples of surface meshes, a little statue of a bunny, a mechanical gear, and a vase that was scanned from an archaeological project. So we want to take these kinds of data and compute useful things on them and transfer mathematical ideas onto this kind of data. And in particular today, I want to tell you about something that I think is really wonderful called intrinsic triangulations. And this is a technique which is not super well known, but what we'll see is that the basic idea is to start with a surface mesh, which encodes a shape, and then draw a set of triangles on top of it and use those triangles for computations and talk about the sort of mathematics of this triangulation that's been drawn on top of another surface. And this turns out to unlock both a lot of sort of really, really beautiful and I think really fun theory, and also lead to some pretty practical algorithms that are fairly impactful for these applications. So the high level here is I'm basically going to split this into three sections. The first of which is just a general intro to surface geometry and some sort of basic examples of the kind of things we want to compute. And then in the second, I'll tell you more about just what these intrinsic triangulations are. And in the last, I'll kind of briefly overview some sort of modern research on that subject and tell you the kind of things we're trying to solve nowadays in this area of intrinsic triangulations. So let's get started with some really, really basic surface geometry. And by the way, I took this to heart to really start from the basics. So hopefully this should really be friendly and straightforward, and hopefully if not too simple. So when I talk about a surface or a triangle mesh, I really mean a mesh which is composed of vertices, edges, and faces. So vertices are like in the graph sense, edges are like in the graph sense. And then additionally, we'll have a set of triangular faces, which are formed by triples of vertices and the corresponding edges. So this is like a graph with a little bit of extra structure associated with it. And then usually the shape will be represented by a set of positions associated with each of these vertices. So for each of the finite set of vertices, we have a location in 3D space associated with it. And then this is how we get these meshes I've drawn on the right sitting in space. We sort of draw the flat little planar triangles between each of its three vertices. And when I talk about discrete surface geometry, this is what I mean when I say discrete, because we're not talking about smooth surfaces. We're talking about surfaces that are parameterized by a finite collection of positions associated with vertices. Go ahead, we got a question?
The mesh already comes with a triangulation.
Yeah, so the question was, we already have this triangles, and yes, I'm sort of assuming that as input, somebody has handed you both this connectivity data, these set of triangles, as well as a set of positions associated with each vertex. And this is a pretty standard data format in these applied areas that engineers work with and whatnot.
And are all your vertices going to be connected by edges automatically, or?
Yeah, so in particular, this will actually come up more later, but normally we'd assume there's like a manifold structure that not just any set of vertex edge and face connectivity is admissible, but in particular, we'd expect that every edge joins two vertices and that the faces are sort of connected up so that each edge has two faces on either side, if that makes sense. So sort of this connectivity really will look like a nice surface rather than having sort of dangling elements or anything like that. Does that answer the question?
Sort of. I mean, what you drew was a complete graph. Every possible edge is there. But you're not going to assume that every edge is every possible. It's not the case.
It's not complete in the sense that there are certainly some vertices in this picture that don't have edges between them, but it is complete that I can't, all of my triangles have been fully triangulated. I can't like add an extra edge inside of every triangle.
Right, okay.
Yeah, because if I did, then I would have like a higher order, like a quad 4-sided face or a 5-sided face or something. So in that sense, yeah, it is fully triangulated. And a really basic example of a thing we might want to compute on this kind of data is Gaussian curvature, which you might have heard of in good old curves and surfaces, which is in Gaussian curvature is one notion of curvature that we might describe for a two surface sitting in 3D space. It's probably easiest to understand visually, just to say that a surface that is either a plane or that looks like a piece of a cylinder, if it's developable, then it has zero Gaussian curvature everywhere. If it looks like a cup, if it looks like a sphere, either pointing inward or outward, then it has positive Gaussian curvature. And things that look like saddles have negative Gaussian curvature. So these are also like planar, spherical, and hyperbolic space. So then you might ask, suppose I have a little piece of some surface and I want to compute a discrete Gaussian curvature. So here's just one, I've drawn a little piece of a surface with one, use this remote. Yeah, there we go. So here I've got one vertex as well as some of its neighbors on a little piece of a mesh surface. And I want to compute some Gaussian curvature that I can then use for downstream computations. And you could imagine a lot of different definitions for this quantity. And in fact, people have cooked up many different definitions with different properties for this quantity. But there's one really useful one that's almost always the right answer. And the way we'll compute this is by saying, well, for all of these triangles instant on my vertex at the tip, let's look at these angles I've labeled theta. So you have a collection of these angles theta I, and then define the discrete Gaussian curvature to be 2 pi minus the sum of these corner angles. So if we do some basic checks here mentally, we'll see that in a plane, sure enough, these angles would sum up to 2 pi. So we get 0 like we expect. In a positive curvature situation, like what's actually shown here in this picture, these angles will sum up to less than pi. So we'll get some positive number for curvature. And likewise, in a saddle-like configuration, which is a little harder to visualize, we'd get a negative number for Gaussian curvature. And to be super, super constructive about how you would compute this, you'd say if I have a position associated with each of the vertices, I'm going to go ahead and label my two extra vertices A and B down here. We can compute vectors, little vectors in R3 associated with the edge from B to A and the edge from B to B. And then we can evaluate this angle theta I just via some grade school geometry as the inverse cosine of the normalized dot product between these two edge vectors. So this is just very, very concretely how you might compute this quantity.
Where did you go to grade school?
Yeah, fair enough. We have one question in the audience.
You said that in the limit, if you take more and more triangles, more and more faces, that definition of curvature looks like the one for smooth surface.
I did not say that, but basically it's true. So the question was, how does this behave under refinement? Basically, if you take more and more a finer and finer triangulation, does it behave similarly to the smooth definition? And basically the answer is yes. The one caveat is that this is sort of a discrete definition only defined at the vertices. So it doesn't even tell you anything about what the Gaussian curvature is inside a face. You'd probably assume it's 0, but this is, so it's kind of like a delta function, right? All of the curvature is right at the vertex. And even as you have more and more vertices, it's always going to be a delta function. You're just going to be stippling the surface finer and finer. So it kind of does converge, but you need to be okay with that notion of convergence. Yeah. So then another idea of the kinds of data we would work with on this surface geometry is gradients and vector fields are sort of standard and useful tools. So you can imagine if you have a discrete scalar function, so a value at every vertex, And here I've drawn these on a triangle. So like on just one triangle, we might have three values, GA, GB, and GC associated with its three corners. Then we can talk about the gradient of the scalar function as being a piecewise constant vector field in each face. So again, this is a discrete gradient operator on a discrete scalar. So I start with a discrete scalar value at every vertex. I apply this gradient operation, and then I get out more discrete data, a little vector in R2 in every face. And if you wanted to be a little more pedantic here, this is really defined in the tangent space of each face, but that's not really an important detail. And if you've ever studied finite element before, this is just standard linear finite elements. But that's not going to be too important for the rest of the talk, so I don't think we should go any farther into this today. One last quantity we like to compute and work with in surface geometry that I want to mention because it's going to be particularly relevant for what comes later is the Laplace matrix. So we hopefully all know the sort of Laplacian from calculus. And of course, we also want a discrete version of this Laplace operator, which for us will turn into a sparse matrix, which is built kind of like a graph Laplacian. So this sparse matrix will have off diagonal entries, these Wij's and Wik's that I've drawn. And the value of these weights in the sparse matrix comes from a formula, which I'm not going to derive today, but I want you to just trust me that this is a reasonable formula, which is for any pair of vertices I and j, you look at the opposite corner angle in any triangle in which they appear. You compute 1/2 the cotangent of that angle, and you add up those values to get a weight for that edge ij. So then you put these in the off-diagonal entries of the sparse matrix, and then you sum up the negative of the row values to get the diagonal entries of the sparse matrix. And you can derive this expression with finite elements if you want to, or a lot of other ways, actually. But for now, I just want you to trust me. And what this means then is we might talk about solving a continuous Poisson problem by saying Laplace f equals g. Well, now in the discrete setting, if I have f and g are now scalar functions, they're vectors holding a value at every vertex. I can multiply times the sparse matrix. I can do some linear algebra. You'll also want a mass matrix M, which is just another matrix constructed similarly. And I can set up a discrete linear algebra problem that describes the same system. And this ends up being actually a super common operation in a lot of those different applications in geometry processing I talked about. Because basically Laplacians and Poisson problems describe smooth functions. And almost always when you're working with real data, you have sort of a belief that whatever function you're computing as output should be smooth. And so for that reason, Laplacians show up all the time in these kinds of algorithms. So this is sort of a linear algebra ingredient that's extremely common and extremely important. And once again, you could write down other definitions of a Laplace matrix for your surfaces, and you could use those in your algorithms instead. But this is really the right one, the right discretization to use in a lot of ways. But one downside is that it lacks a maximum principle. And the maximum principle is something we might have heard about for Laplace systems, which is that extrema occur only on the boundary in a solution to a Laplace problem. But this discrete matrix, if I do some linear algebra to solve a Laplace problem, that's actually not necessarily true for this discrete matrix. And that's really unfortunate. And it turns out to cause some problems in our downstream algorithms. So we're going to come back to that later because we have a way to fix it. But one last thing I want to say here is that a really annoying issue in practice to which millions of hours of engineering have been dedicated is that not all meshes are equal. And it turns out when we're doing these kinds of computations in practice, a lot of algorithms work great on these meshes that have nearly equilateral triangles all over the place, and work terribly on these meshes like on the right that have lots of very skinny, acute, and lots of very obtuse triangles in them. And there's a couple reasons why. One is that skinny triangles tend to lead to bad conditioning for numerical problems. So if you're doing like an iterative method, it'll take a lot of iterations to converge, and this is annoying in practice. And also having obtuse triangles means that when you compute these discrete gradients, there's a lot of approximation error in the discrete. You get a very inaccurate discrete gradient. And this again causes problems downstream. So a sort of gigantic problem in this field is how do we make computations work better on these meshes that have lots of skinny triangles in them, or that otherwise just are not nice, nearly equilateral meshes. And it really, there's a lot of kind of folklore around what makes a good mesh, but this paper, What Makes a Good Linear Finite Element by Jonathan Shuchuk is really awesome reading on this subject if you happen to be interested. And generally speaking, you can't just assume you always have a nice mesh because they basically just don't exist. Because even if you add lots of triangles to your mesh to give it these nice little equilateral elements. Well, you might have to add a whole lot of them to get them. So on the leftmost side here, I get my thingy. There we go. On the leftmost side here, we have this mechanical gear model, which has been described using just 3,000 triangles, which is a pretty concise representation. It'll lead to efficient algorithms when we run them on a computer. If I try to make these triangles equilateral, I have to create 300,000 of them to get a nice equilateral set of triangles. And now my computations might be infeasibly expensive on my computer. Conversely, if I say, well, let's just make the best mesh we can with nearly equilateral elements on the right, you can do that, but the approximation suffers. We've no longer described the same shape. So it really is useful to be able to work directly on these meshes that might have skinny triangles in them, because we just can't expect to always have nice triangles in our meshes. And here are just two examples that we'll both see later in the talk. Oh, knocked my microphone off, 1 second. Where we take algorithms that work perfectly well on meshes with nice triangles, we run them on a mesh with bad triangles, and it outputs nonsense. So let's try to do some beautiful mathematics to address this problem and see what kind of solutions we can find that change the picture a bit. And there are many methods to do this, but the one I want to tell you about is a set of techniques called intrinsic triangulations. So let's come back to this example of computing Gaussian curvature. You might have heard of Gauss's theorem egregium. My Latin's not too great, so don't mind my pronunciation of that. But this was sort of one of the most celebrated theorems of Gauss, which is that this quantity, which we now call Gaussian curvature, I don't think he called it that, is determined only by the lengths and angles along the surface. So the way we visualize this Gaussian curvature and the way we think about it, you would think it depends how the surface sits in space. But it turns out, actually, if all you can do is measure lengths along the surface and measure angles along the surface, that's enough to fully define the Gaussian curvature. And these quantities that depend only on lengths and angles along the surface, not how a surface sits in space, we call intrinsic quantities. And this is really beautiful and sort of unlocked the modern era of differential geometry, where we describe surfaces by their metrics and by lengths and angles along the surface, rather than how the surface sits in space. However, when we talked about this definition of discrete Gaussian curvature, I gave a computation that definitely depended how the surface sits in space, right? It involved the positions of these vertices, which is an embedding. So you might wonder, can we do this discretely as well? Can we talk about a discrete surface solely in terms of lengths and angles without any reference to how it sits in space? And sure enough, you can. It's pretty easy. The idea is that instead of representing geometry by an embedding, a position associated with each vertex, we'll represent the geometry by a length associated with each edge instead, and have no notion of vertex positions anywhere. So then, for instance, if we want to compute the Gaussian curvature at a vertex, well, we can take our triangle here, and as I said, we know the lengths of the three edges because that's the data we have. We can measure the angle of the corner of the triangle, again, via some grade school geometry, depending on where you went to grade school. And I didn't show the manipulation, but this again is just being a different expression that you get by rearranging the cosine rule. And you get that these corner angles theta I are now the inverse cosine of an expression involving the three edge lengths of the triangle. And then we can still compute the Gaussian curvature just as we did before, as 2 pi minus the sum of these interior angles. And this is really cool because now our discrete computation has mirrored this beautiful result from the smooth setting, that by working with only lengths, we get a different discrete expression that computes the exact same quantity, but doesn't depend at all on how the surface sits in space, just on weaker data, which is a length associated with each edge. So this is actually the whole basic idea of intrinsic triangulations. So to make this really concrete, what we're saying when I talk about intrinsic triangulations is talk about surfaces, not with a position associated with each vertex, but with a length associated with each edge. So whereas before we had connectivity and vertex positions, let's throw out those vertex positions and just do connectivity and edge lengths instead. And I'd be remiss if I didn't at least give a nod to sort of the historical context here. So intrinsic triangulations go way back to Regge and were initially used a lot actually to formalize computations and some cool constructive proofs in general relativity. There's sort of a renaissance in the 90s and the early 2000s where the theory of something called Intrinsic Delaunay triangulations was developed. And more recently, there's been a lot of really cool work relating these triangulations to conformal maps and conformal geometry and circle packings, although we're not going to talk about that too much today. So When I first described this, it probably just sounds like an arithmetic trick. It doesn't sound so interesting to take a computation of position and like arithmetically reparameterize to a computation of length. But the crazy thing that happens is that when we make this change, we actually move to working in a much larger and more general space of triangulations. And that unlocks a whole lot of new theory, and it unlocks a whole lot of new algorithms for us to build upon in this domain. Oh, I think my build got a little broken here when I exported, but that's fine. Yeah, don't mind these words being on top of each other. I can read what they're what they say here. Sorry about that. So usually we think of Euclidean triangles, just again in the grade school sense, a triangle with straight lines, as being defined by having straight edges. So we have 3 vertices with straight edges between them. And when we talk about this on surfaces, we're going to translate this to meaning the edges of the triangles are geodesic paths. I'm going to use the word geodesic a lot in the next 45 minutes. So geodesics on surfaces is like a path that's locally shortest. So it's been pulled as tight as it can. So they basically are kind of like straight lines along a surface. And also the Euclidean triangles we're used to working with have flat interior, which on surfaces just means that there are no vertices on the inside of any triangle. And the reason that this is a big deal is because this funny bent triangle that I've drawn here on the right actually meets this description, right? So its edges are geodesic paths. If you look at the edge from I to K, for instance, it's locally shortest. You couldn't pull that edge any tighter, and none of the vertices of the underlying domain lie on the inside of the triangle. And what this means is that if I tell you the 3 edge lengths of this funny bent triangle I've drawn along the surface, I could lay out that triangle in the plane, and its shape in the plane is totally unambiguous because a triangle shape is determined by its 3 edge lengths. And I could start computing things about that triangle. I could measure the area of that triangle. I could measure the length, the distance between 2 points inside that triangle. I could measure the angle of a little wedge drawn inside that triangle. And all of those quantities I would measure would exactly match what I would get if I were to evaluate them on this bent triangle sitting on top of the cube. So even though this triangle is funny and it bends along the surface because it has geodesic edges and no curvature on its interior, then I am really computing with the true metric of the underlying surface by computing with this triangle. And again, I can describe it just by 3 edge lengths. So there's a whole zoo of quantities you can compute just with these triangles, given their edge lengths, things like areas and angles, Gaussian curvatures we already saw, as well as other things like distance. You can work with Laplacians and tangent vector fields and a whole zoo of intrinsic geometric quantities. We'll use the word extrinsic to basically mean the complement of all this intrinsic stuff. So extrinsic just means all the things that aren't defined solely by the notion of lengths and angles. And these will be things like the normal, the outward normal of the surface, or another notion of curvature called the mean curvature. But we aren't going to talk about those anymore today. A quick call out here, just in case there are any differential geometers in the crowd, that there's a notion in differential geometry called a cone metric, which is to say that the metric of this surface is Euclidean everywhere except at specified cone points. And that's exactly what's happening here in surface geometry, that at the vertices of this mesh, something interesting happens in the metric, and everywhere else it's just Euclidean. So what that means is that the edges are actually totally incidental because they don't show up in the metric at all. So we should have the freedom to change which edges we've drawn while preserving the same metric. And that's what we're doing with intrinsic triangulation in sort of the language of differential geometry and cone metrics. So to start giving some intuition for why this moves us to a larger space of triangulations, well, we can start with sort of the low-hanging fruit, in that there are some intrinsic triangulations described only by edge lengths, which cannot be embedded in R3 with straight lines. So here's a really simple example where on the left, I've drawn intrinsic metric where you can imagine a length associated with each edge. But on the right, there's no way to actually embed this thing in space because the 3 copies of the vertex I, their little arms aren't long enough and they can't reach together to touch in the middle. So of course, if you were willing to consider other notions of embedding, like a non-piecewise-flat embedding or an embedding in a higher dimensional space, you might be able to make this work. But with a piecewise-flat embedding in R3, there's no way to embed this metric. But if we just talk in terms of edge lengths, it's no problem. But actually, it gets a lot more interesting than that. You can ask yourself, suppose I have some domain, some surface that I care about, and I want to know how many possible triangulations there are of that domain. So if I have a triangulation that's embedded, that's sitting in space, you can ask, okay, how many ways can I connect up those vertices with triangles to realize the shape that I care about? And the answer is just one, right? If I took these same vertices on the shape here and drew any other triangle between them, then I'd be describing a different surface. So this is my only option for triangles to draw. But if we play the same game in the intrinsic setting, so here my domain I care about is a cube, and I've drawn one set of intrinsic triangles along the cube. And then I can draw another set where here the triangles start to have some of these funny bent edges. So like here, if you look sort of in the center here, right, you can see there's one triangle that touches these two vertices in the opposite corner and is bent over the edge. Here's another intrinsic triangulation of the same domain. And if you keep doing this twisting motion, then by construction, we create an infinite family of triangulations, all of the same domain. And this was just with one twisting motion. So by moving our thinking from the stronger embedded setting to the weaker intrinsic setting, we move from there generally being just one triangulation to there generally being infinitely many triangulations of the domain. So maybe this gives some intuition for why this is exciting and why it opens up a lot of new things we can do. In particular, we can traverse this space of intrinsic triangulations of a particular domain with a little elementary operation, which we'll call an edge flip. This has about 1 million names in different areas of mathematics. It gets called like a bistellar flip and a swap move and a bunch of other things, but I'm going to call it an edge flip. So an edge flip just means we look at two triangles that appear in our mesh. So here I've drawn the triangles on the left, IJK and IJM. And then we're going to exchange the edge IJ for the opposite diagonal IK. So now we get two different triangles, IKM and JMK. So really concretely, computationally, to do this operation, you would want to update your mesh connectivity, these set of vertices, well, the vertices don't change, so you'd want to update the edges and faces to reflect this change. And you'd compute one new edge length, this LMK, along the opposite diagonal. And again, this is just elementary geometry. If I gave you the lengths of the 5 edges on the left, you could sit down at a whiteboard and figure out the expression for this new diagonal across between L, M, and K. And what's happening if you sort of repeatedly do these edge flip operations is that you construct these long, interesting bent triangles along the surface. So usually we'd sort of initialize an intrinsic triangulation to be the usual, the extrinsic or the embedded triangulation of the domain we started with. Then we forget the vertex positions, keep only the edge lengths, and start doing these edge flip operations repeatedly. And what happens is we'll create these long, interesting bent triangles along the surface and sort of traverse the space of triangulations. So to recap here, just because this basic idea of intrinsic triangulations, at least for me, it took me a long time to sort of wrap my head around this, and I want to make sure we're sort of on the same page. So the basic idea is to encode the geometry of a surface by a list of edge lengths rather than vertex positions. And this is enough to do a whole bunch of geometry on the surface, even though you don't have an embedding. And we can use edge flips to transform amongst these triangulations. So I've drawn a picture on the right here to be really clear that because we're talking about edge lengths, I don't mean constructing a new edge like you see on the left that just directly connects the two vertices. I mean doing an intrinsic edge flip, which implicitly creates this funny looking bent edge along the surface. And doing these intrinsic edge flips, this is maybe the most important part, exactly preserves the geometry. To be a little bit more formal, this edge flip operation is an isometry between the metrics induced by gluing the triangles together. Because all the other triangles don't change, and the two triangles that participate in the flip, well, it's kind of clear just visually that there's an isometry between the metrics before and after. So this means if I want to compute some geometric quantity along the domain, it will be exactly the same after any sequence of edge flips. So I have the freedom to sort of edge flips to my heart's content to create more interesting and more useful triangulations. And here's sort of an example of seeing this in practice. So this is a style of visualization we'll see a few times more coming up. So let me first tell you just how to read the visualization. So here, the black wireframe, which hopefully you can see well enough, is the mesh we started with. So it's a triangulation embedded in space that might have, I think this is a mechanical part that was made for some CAD modeling application by some engineer. And then the brightly colored triangles sitting on top are the intrinsic triangulation that we've constructed along the surface, which follows these rules I described earlier, that all of the edges of the colored intrinsic triangulation are geodesics, and that no vertices of the underlying domain, no cone points, no curvature appears on the inside of any triangle. So a cool thing happens here. Remember I said that skinny triangles and small angles are a problem. Well, at the beginning, this initial black wire frame has all of these incredibly acute skinny triangles at the tip, and this would cause our computations to go absolutely haywire. But by building this nicer intrinsic triangulation, we exactly preserve the geometry of the domain. We're working on exactly the same metric, but we've now created a triangulation that has less skinny triangles. And now all of our computations will work better, and this will make our engineer friends very, very happy. Okay, so in particular, there's a really, really special and important intrinsic triangulation that we can construct. And I'm going to tell you what it is now. So remember this Laplace matrix? I said that it lacks a maximum principle. And really this happens when these weights, these 1/2 cotangent theta Wij's that we compute along an edge ij, they can be negative, right? So if you imagine in an obtuse triangle, if the angle theta is greater than 90 degrees, then cotangent of theta is a negative number. So we get these negative weights Wij in this matrix. And those weights are exactly what causes the failure of a maximum principle. So we'll say that if an edge has a positive or a non-negative weight Wij, so if the angles of the opposite edges are greater than 90 degrees, then we'll say that this is a Delaunay edge. And if all of the edges in the triangulation have this property, then we'll say that it's a Delaunay triangulation. And you might have heard this term Delaunay from computational geometry and other areas of mathematics before. And this is just sort of a natural generalization of that idea to surfaces. But this cotangent construction is the useful construction to work with. So we really want our triangulations to have this Delaunay property, to have the property that all of these cotangent weights, these Wij equals the sum of 1/2 cotan theta, are positive, because that will give us a Laplace matrix that actually does have a maximum principle and has a lot of other good properties as well. So now to the punchline. If you want to build an intrinsic Delaunay triangulation, so you want an intrinsic triangulation of a surface that has this Delaunay property, there's a really simple constructive procedure. You just identify any edge in the triangulation, which is not yet Delaunay, which has a negative weight, and you do an edge flip. And the absolutely beautiful proof that came out of a series of work eventually in Bobenko and Springborn in 2005 is that this procedure is guaranteed to terminate with an intrinsic Delaunay triangulation. So here's an example of seeing when I do this in practice. So again, I've taken another one of these engineering mechanical models given by the black wire frame. If I were to compute directly on it, it wouldn't work well. But I run this algorithm. I just repeatedly identify any edge that's not Delaunay and flip it. Then eventually I get out this other triangulation given by the colored triangles. But remember, my representation is just a list of edges, a list of edge lengths and some mesh connectivity. And this flipping procedure terminates with this colored intrinsic Delaunay mesh. And now I can go do my computation, build my matrices on this mesh instead, and everything just kind of works better. So a quick proof sketch, just to give an idea of how we actually prove that this property works. So we claim that this greedy Delaunay edge flipping algorithm terminates. And I say greedy because we're not being clever. We're not planning ahead. We're just picking arbitrarily any edge that isn't Delaunay and flipping it. The way that we argue that this converges is to consider a quantity called Buson's harmonic index, which is defined here on the right as for any triangle, you take the 3 edge lengths and you add up the sum of their squares, then divide by the area of that triangle. That gives you the harmonic index of one triangle. And then, oh, my builds got out of order. And then you add up these harmonic indices for every triangle to get a harmonic index for your whole triangulation. And you can show by a computation that anytime you flip one of these non-Delaunay edges, that this quantity decreases. So we've identified a quantity that's decreasing on this during this greedy process. Now we just need to argue that we don't flip forever. We don't like asymptotically get closer and closer without ever getting there or something like that. And the way to show that is that you can argue that there are a finite number of triangulations with bounded harmonic index. So it's always going down. There are only so many triangulations with harmonic index less than a certain number. So as long as we're always moving down, it must eventually terminate. And since the procedure is defined by flipping an edge whenever it's non-Delaunay, then when it terminates, they must all be Delaunay. So this is really beautiful. And the result that's proven in this intermite, which is kind of what the whole thing hinges on, is that on any surface, there are a finite number of geodesics. These edges are like geodesic arcs. There's a finite number of geodesics less than a given length. And once you know that, then you can sort of build up everything else you need. Cool. One thing you might wonder about is we've proven termination and existence. The question is it also unique? The answer is in general position, yes, but occasionally in special configurations, no. So for instance, on a symmetric shape, it might not be unique, or more generally, anytime you have 3 vertices that lie on a common circle, so 3 co-circular vertices, then there will be, the Delaunay triangulation will not be unique. There will be a small family of Delaunay triangulations. Cool. So these Delaunay triangulations are so amazing and so useful because there's a gigantic zoo of different properties that are all true about them, that are not true about other triangulations. So we used as our definition that they have non-negative cotan weights. And let me rattle off a whole list of these amazing properties now. This also means that at any edge, the sum of the 2 opposite angles is less than pi. This means that every triangle has an empty geodesic circumcircle. This means that the set of edges in the triangulation contains an edge between each vertex and its nearest neighbor. On Delaunay triangulations, so if you consider the set of all possible triangulations of a domain, the Delaunay triangulation is the one that maximizes the minimum corner angle in any triangle. It gives you the smoothest piecewise-flat interpolation. So if you look at these gradients I mentioned before, the norm of the gradient is the smallest. You get this maximum principle for the Laplacian. If you looked at the eigenvalues of this Laplacian, they're minimized. Gives you the shortest minimal spanning tree, and it's a geometric 2-spanner, which means that if you consider the distance along the edges of the graph of this intrinsic triangulation, it's at most twice the actual geodesic distance between 2 points. So we get all of these magic properties that are true about intrinsic Delaunay triangulations, and now we can start building on top of them for all of these algorithms we might want to run. And this is really important too, because if you don't use this intrinsic machinery, if you try to play these kinds of games with embedded triangulations that sit in space, none of these properties are true. There's no definition that makes all of these properties go through. We really need to sort of follow in the footsteps of Gauss and Levi-Civita and move to the intrinsic setting in order to find this beautiful definition that makes everything line up. Another way to understand this, if you have more of a sort of finite elements mindset, is to say that, as I said before, improving these minimum angles and reducing obtuse angles improves approximation. And really what we're doing is just constructing a better set of basis functions along the surface. So sort of in a finite element sense, your set of triangles for a domain really defines basis functions when you interpolate data within those triangles. And by building a better set of triangles, we're building a better basis for interpolation, and that's sort of what makes everything go better. One other sort of tricky detail that I think is kind of interesting is that when doing these edge flips, you might find yourself creating an edge that connects a vertex to itself, that wraps around a handle of the shape or something like that and goes from a vertex to itself. This is kind of crazy. Formally, what's happening is that we're reducing the topology of our triangulation from being a simplicial complex to merely being a delta complex, where delta complex is basically just allows for things like edges, self-edges in the graph. So here I've drawn two examples down on the bottom of domains where we have delta complexes that are not simplicial complexes. So on the lower left is a torus with only one vertex. So we have 2 triangles, and in each of those triangles, all 3 of the adjacent incident vertices are just this one vertex I. So sort of logically, if you follow the gluing instructions, this defines a torus. Then on the right, there's a cone where the base of the cone is a self-edge from vertex J to itself. So this is really scary. And I think that this is one of the reasons that this structure sort of did not receive as much attention from the engineering community and things like this, because this property kind of scared people away. Because if you don't allow this to happen, if you don't allow for these self-edges, then all those properties I just listed are not true. So because people were sort of afraid to work with this more mathematically scary object of a delta complex, it sort of delayed investigation into this. But in practice, aside from making some of your proofs a bit harder, everything basically works out. It's okay to have a self-edge in your triangulation. Yes, absolutely. So the question was, can you just subdivide? And the answer is 100% yes. In fact, so after 2 rounds of regular subdivision, so taking every triangle and doing like a triforce thing and replacing a triangle with 4 smaller triangles, after 2 rounds of that, every delta complex becomes a simplicial complex. So that would be a factor of 16 increase in the number of edges, which is annoying, but not that bad, as you say. Great question. So you can also go a bit further. This is a little bit more on the computational algorithm side, so I won't go too far into this. But beyond just flipping edges, you can also start inserting new vertices to make your triangulation better. And in meshing literature, this is called refinement. So if you start identifying triangles that you still don't like, even in the Delaunay triangulation because they're too skinny, you can insert new vertices and it generate these really beautiful meshes like the one I've shown on the far right, where not only does the triangulation have the Delaunay property, but also you have this nice uniform distribution of triangles. And this is exactly what people in the meshing community want to have. So really quick, just call out to sort of put my results where my claims were in terms of these algorithms and these applications. Here are two quick examples of cases where this really does do good things in practice. So here's an algorithm called the heat method, which is used as a fast approximate algorithm for computing geodesic distance on surfaces. And if we run it naively on this CAD model of a rocket ship, it outputs basically nonsense because of all these skinny triangles and the triangulation. Just doing this intrinsic Delaunay flips thing first drops the error by a factor of 3. And now we get something that actually looks like a distance function. So that's good. And doing this intrinsic Delaunay refinement now at a cost of barely doubling the number of vertices gives an extremely accurate solution with an error of less than 1%. So this makes us very happy if we're trying to compute with this kind of engineering data. Here's another example where I'm solving an interpolation problem on vector value data. So what's happened here is along the boundaries of this shape, I took the outward normal vector along the boundaries as boundary data, and I want to interpolate to construct a smooth vector field on the interior that satisfies that boundary data. But if I do this naively using the Laplace matrix, what ends up happening in this image I've shown here is we get some vectors that I've circled in red that actually point the total wrong way. They point in the opposite direction of where you'd expect them to point. And this is happening because of the lack of a maximum principle in our Laplacian. But if all we do is swap out the normal Laplace matrix with this intrinsic Delaunay Laplace matrix we get from edge flips, all of a sudden everything works better and we no longer get these flipped over vectors. Cool. So now as we sort of start to get towards the end here, I want to just show a few examples of things we're looking at, like future directions in this area and what recent research looks like. So one question to ask is, what if we do have non-manifold data? We got a question at the beginning of like, just how bad can this connectivity be? And sometimes data you encounter in engineering has atrocious connectivity, it's non-manifold and all these things. So it'd be great to be able to compute with it. And if we want to pitch this to our engineering friends as a magic black box that builds a better Laplace matrix, well, we really ought to be able to work on data, even if it happens to have a few non-manifold edges. And I've been name dropping this word non-manifold in case we're not familiar with it. So a manifold vertex or a manifold surface is basically one that looks like the plane locally. So on the upper left is a manifold vertex in a mesh, and on the lower left there is a non-manifold vertex at the center in this hourglass configuration because it's not locally homeomorphic to the plane. And similarly, we can talk about non-manifold and manifold edges. So this sort of starship triple configuration is not homeomorphic to the plane. And these show up fairly often in science and engineering, sometimes as bugs, sometimes they're because they're actually what we want to compute with. But the big problem is that you can't flip these non-manifold edges. It's just sort of clear looking at it visually, like what would the flip operation be on this? So then this whole sort of tower we've built up of intrinsic Delaunay edge flips and this high quality Laplace matrix, this whole tower comes crumbling down because we can't do this operation on the non-manifold edges. So the resolution is a common trick in mathematics, which is to build an appropriate covering space, do our computation on that covering space, and then pull the result back. And in particular, we cooked up a covering space that we call the tufted cover. And the way you do this is I'm going to tell you how you construct the tufted covering in a second, but we construct the tufted covering, build the intrinsic Delaunay triangulation of the tufted covering, compute our Laplacian or do whatever other constructions we want to do there, and then pull it back to the original surface. And I call this the tufted cover because I think it kind of looks like the buttons on like antique furniture, these tufted buttons. So we call this the tufted covering of the domain. So the way to define this tufted covering is to say for each face in your triangulation, let's split it into two copies. So we've got a top and a back copy of our face now. And then for each edge, remember all the adjacent faces have been split into two copies. We're just going to walk around and glue consecutive copies together along their shared edge. So again, we create a front and a back copy here. Then we walk around this edge, gluing along the shared edge, front to back, front to back, front to back, and we repeat this gluing procedure at every edge. And this gives you a crazy new triangulation, a discrete covering of the surface, which we call the tufted cover. And here I've got a video which hopefully is playing decently well over Zoom. So here's a really, really simple non-manifold mesh, which just 3 faces meeting at one non-manifold edge. And as we said in the middle here, this, there we go. This middle edge is not manifold because it's not homeomorphic to the plane. So what we'll do is we'll take each face and split it into 2 copies and then glue those copies together along the shared central edge. And now what's happened is that our PowerPoint does not like my movie transitions. There we go. So our one non-manifold edge has become 3 manifold edges. And by the way, I've drawn this with the faces sort of bubbled outward, right? It's not like a triangular surface, it's this bubbled outward surface. This is just for visualization so that you can see it. Geometrically, when we compute with this thing, we still think of it as being the flat triangles we're used to. So now we can do these intrinsic Delaunay edge flips. This one happened to have one non-Delaunay edge, and we get an intrinsic Delaunay triangulation of the tufted cover. So what's happened is that by this covering construction, all of our non-manifold edges turned into multiple manifold edges. So we're good to go. We can do our edge flips. We actually created non-manifold vertices all over the place by this construction, but that's a non-issue because they turn out not to be an obstruction for using intrinsic triangulation. Non-manifold vertices are fine. It's the non-manifold edges that were a problem, and we got rid of all of those. So now we can really make good on this promise. If you had any triangle mesh that you want to do some computation on, you build this tufted covering of the surface, compute the intrinsic Delaunay Laplacian there, and read off the Laplace matrix. The tufted cover is a double cover of the domain we started with. So all you have to do is divide by 2, and now you have a Laplacian for your original surface. And you can use this in whatever algorithm or whatever computation you might be doing. Again, some quick examples just to show you the kind of things this is useful for. One place the Laplacians show up is computing minimal surfaces. So things like soap films, and soap films are particularly interesting because they're often form non-manifold configurations. So if you want to run an algorithm to compute a minimal surface on a low quality mesh, sometimes you didn't even knowingly start with a low quality mesh. It just showed up as an intermediate quantity in your computation. Using this Laplacian will give you a lot of robustness to these poor quality triangles. And also having a maximum principle makes a lot of sense because we know that minimal surfaces should have no extrema. So having a Laplacian that sort of discretely inherits the smooth property we expect makes a lot of sense. Here's one more fun one for something called differential surface editing that shows up a lot in like animation and video games and movies and things like that. So in differential surface editing, you have some shape and you want to smoothly pose it into a new configuration. So here's a model of a goose, and the way the animator constructed it was kind of lazy, I guess, so that it has skinny triangles. It has every edge marked in red here as a non-manifold edge. So it's a very low quality, even though it looks like a goose, it's a very low quality mesh of the goose. And if the animator tried to use this algorithm to pose the goose into a new configuration, you would get numerical nonsense if you do it using the ordinary cotangent Laplacian. This would not look good in your Pixar movie. You get the idea. If all you do is you take this Laplace matrix and swap it out with this intrinsic Delaunay Laplacian built on the tufted cover, because this thing was non-manifold, all of a sudden the algorithm works as expected and we can pose the goose into interesting configurations. To be a little bit more formal here, this intrinsic Delaunay Laplacian on the tufted cover gives us a hard guarantee of bounded interpolation. So what I mean is that here I've got an example of a triangle mesh, and there's sort of nothing up my sleeve here. This is really just a triangle mesh sitting in the plane. And I have values defined at 2 points. So I've got phi equals 0 and phi equals 1 at 2 points. And I want to interpolate that data smoothly to the rest of the domain. And a basic guarantee we expect when interpolating data is that the output is bounded, that if my inputs were bounded between 0 and 1, after interpolation, all of my outputs should be bounded between 0 and 1. But if I do this interpolation naively with the normal Laplace matrix, this doesn't happen. You get values much greater than 1 all up along the top region of the shape, which seems kind of ridiculous. And even using normal Delaunay triangulations doesn't help, because the obtuse triangle that's causing a problem is on the boundary, and we can't flip or do anything about these obtuse triangles on the boundary. But if we construct the tufted covering of this domain, well, now we can always flip every edge, and we get this hard guarantee of bounded interpolation for harmonic interpolation problems with no restrictions about boundary data or anything like that. So this is sort of a useful primitive. If you're a student of PDEs, you might know that imposing point constraints on harmonic interpolation problems is actually not well posed because it doesn't converge under refinement. But nonetheless, this is a super common thing to do in practice. So sort of giving this algorithm a discrete guarantee of sanity is a very useful thing for us to do. So I want to wrap up here too with sort of two unsolved problems that I and other people are working on, just to maybe stimulate some discussion in case anyone here has ideas, and we can chat about how to solve some of these. So one question is this Delaunay flipping algorithm. It's great, it's super useful. It's increasingly being used in all of these applications I talked about. But you might wonder, how many of these edge flips do you have to do to reach the Delaunay mesh? Because all I did was I proved that it terminates, right? I didn't tell you anything about how quickly it terminates or how many flips it takes. And the worst case bounds are extremely pessimistic, but if we sort of benchmark this on data, so here I took 10,000 meshes from a data set of engineering models, and for each one I counted how many flips it took to reach this Delaunay mesh. So each dot is a mesh from the data set. The lower axis is the number of edges, and the left axis is how many flips it took to get to this Delaunay triangulation. It's basically linear, and that's great news, and this is why we're happy to use it in practice. But there's this giant gulf between what we observe in practice and what we've managed to prove thus far. So as in that plot, this takes an asymptotically linear number of flips. This O of n notation just means asymptotically it's linear. The worst known counterexample, there's a family of meshes in which it takes a quadratic number of flips. But the bound we get from this proof is exponential. So there's this giant gulf between the worst known counterexample and the tightest bound. So this is a really, I think, important question to consider if you want to convince people to use this. And also it'd be good to know just what it is about average case meshes that makes them much better than the worst known counterexamples. And this would be a very useful thing to quantify somehow. I'm going to skip this because it takes a while to explain. Our last question is there a rational representation for intrinsic triangulations? So another problem we encounter in practice is that computing with real numbers on computers is very imperfect because of something called floating point. Computers can't actually work with real numbers. They work with approximations of them and things go wrong. So if we want to write down algorithms for computing with bad 3D data that always work, we want to be immune to these problems of computing with real numbers on computers. So in particular, you might find, and I have found, that if you take an engineering model and run this edge flipping algorithm, it might not terminate. It might just run forever, not because our math is wrong, but because our floating point computation has failed us. So an elegant solution is to say, instead of working with the reals, let's work with the rationals. Let's take our input data and just project it onto the rationals, do all our computation in the rationals instead of in the reals. But it's not that easy, because these edge flipping operations are not closed under the rationals. If you take a mesh with all rational edge lengths and you do an edge flip, you don't necessarily get a rational edge length out. So sometimes though, people get over this by reparameterizing, by saying, oh, instead of representing the edge lengths, let's represent the log of the edge lengths or something like that. And often it turns out that with the right reparameterization, you do get a closed rational representation. Haven't been able to find one yet. Or maybe the opposite is true. Maybe we can somehow make like a counting argument or a dimensionality argument that there can be no closed rational representation. And that would be sort of equally beautiful and would also at least allow us to stop the search for a rational representation. Yeah, so with that, I'll wrap up and leave a little bit of time for questions here. Of course, a lot of this work and these slides and this were from some of my wonderful collaborators. And if you're interested, we actually just put together a 3-hour course on this topic. If anyone's interested in a more formal and more in-depth run through, as well as lots of software you could download and play around with if anyone ever wanted to generate or visualize an intrinsic triangulation. So yeah, thank you all very much for listening. Hopefully we can continue to chat over the months to come. And I'm ready for any questions.
Okay, thank you very much, Nick. That was extremely nice. Oh, does anybody have any questions?
The question is, with what mesh are you going to start in the beginning? I mean, the position or the lengths that you get is important, I suppose.
Yeah, absolutely. So the question, I don't know if the mic came through there. So the question is what about this mesh you start with in the beginning? Is it important? Can you change it? How does this affect the whole situation?
And how do you get it in practice?
Yeah, so the most boring answer is the answer in practice is that engineers, people who work in all of these domains have data sets of these meshes. Maybe you have a 3D scanner, you waved it around the room and you scanned your object. maybe you're a mechanical engineer who sits there on the computer using computer design software to construct these meshes that model important mechanical parts. These things come out of CT scanners and protein imagers and things like that. So these are, in practice, usually our sources of data. So these are, of course, all embedded meshes that sit in space. Then we just take them, we forget the vertex positions and read off the edge lengths. And now this is our intrinsic triangulation that we start computing with. So that's the practical answer. Another question, though, is where else might you get one from? And then there's at least one really interesting answer there that I think is really exciting, which is that suppose you have you want to work with anisotropic metrics or anisotropic shapes, so shapes that where the metric is skewed in one direction and notion distances measured are longer in one dimension in one direction than in the other. What you can do then is you can take any set of edge lengths and just rescale them according to an anisotropic metric and start computing with that. And this is actually a really exciting thing to do in practice because there's no corresponding operation on an embedding. It's not easy to take an embedding and skew it according to deformation of the metric along the surface. So I think there's a lot of sort of open directions to go in by playing games with your metric to construct new sets of edge lengths and then computing with those instead. So that, did I answer the question somewhat? Okay, a bit.
Given that your data often comes from things which have been scanned, does that mean that you're kind of working with a computable subset of the reals for your coordinates of your data points with that?
Yeah, absolutely. So usually these would be floating point numbers, like in particular, which are a finite sized representation that basically looks like scientific notation. You can imagine taking if you have scientific notation that's like 3.5 times 10 to the 7th, you take 3.5 and represent it with a finite number of values. You take the exponent, you represent it with a finite number of values. These are floating point numbers, which is what your computer is using internally. And surely pretty much any scanner in existence is going to be mapping onto this subset in the data it hands you. Yeah, so then I guess the question is the continuation would be, what can you say about this subset of the reals and how can you bound computation on this floating point subset of the reals? This is something, this is like a whole subfield of numerical analysis. Generally, the results are unsatisfying though, and that there aren't great results about, with the exception of a few very specific computations, you can't really bound that the output of a long series of computations will be correct even on this limited subset. Unfortunately, the world would be a much better place if you could. Anything else?
Maybe to come back to my first question, suppose a mathematician can pick the initial configuration. Can you then give conditions on it, for instance, where then you would know that the Delaunay algorithm has a good complexity? I mean, better than you know now. So now it's exponential, right?
Yeah.
But suppose that you pick a clever starting configuration, can you then do better?
I think that's a great question. I think that'd be exactly the kind of property you'd want to prove about this to make it go through. I don't know any answers yet.
Because I suppose a counterexample is like a bad starting configuration.
Yeah. So in particular, actually, the slide that I skipped there is basically to say, if you take this twisting cube example again, because you can keep twisting forever, that means that you can construct counterexamples which are arbitrarily far away. So actually, if you define the input to allow any of these as input, then you know already there can be no bound. Because you can always just twist a few more times, get even farther from being the Delaunay triangulation. So what this tells you is that somehow you have to limit the class of input you're allowing to say anything useful. So already usually we'd limit our class of inputs to only those which can be embedded in R3, or which might have come from some straight line embedding in R3. So that's what disallows this infinitely twisted cube as we already consider it. But I think it's a very important direction of attack to think about other constraints you might put on the input, or even identify any class of input triangulations for which bounds are easier to come by. Yeah.